Guys, the usual, please. Give me some energy. Good afternoon.
Good afternoon.
That's good. Now, so today it's not a formal meeting. First of all, it's just a bootcamp to sort of refresh your knowledge on some calculus and some other things. So probability and stuff like that. So now this will involve lots of note taking, guys. So why don't you, if you want to keep note of this, take your notebooks, pens, whatever you have to take notes. And let me get started. So I want to start with this notion of function, right? So you've probably seen functions before, right? In your calculus classes, whatnot. So what is function? So function is basically a mapping from one set to another. So it usually maps set of x, and this can be very general, into set of y's. Now, set of x we usually call set of arguments. And set of y's we usually call set of values. Okay, now it's not just some arbitrary mapping, there are some properties. So now I'm going to write some symbols and let me know if it doesn't make sense to you. Okay? So for any x, which is an argument, oh, you're coming to help us with the projector. Okay, wonderful. All yours. For any x, which is an argument, and that argument has to be from the set of arguments. So I'm writing this. There exists unique value y from the set of y's. Now, guys, you can see that there are some. So I see some of you kind of trying to look carefully at this, and right? You think this all right?
Yeah, I just forgot my glasses.
You just forgot. Okay. Well, so guys, does it make sense to you, these symbols? Have you seen it before? This A upside down? No? Who's seen that before? Okay. 1, 2, 3. Who have not seen that before? Okay. And similarly is this. So it's kind of E letter turned mirror. Okay. Now, so this is basically just the way to write mathematically stuff. Okay. So this is called for any. Okay. So this means, and this is literally letter A upside down. That's what it is. And what it means is for any x. So this. Have you seen this before? This kind of symbol. Have you? Okay. So I see more consistent response here. So this basically means belongs. Okay. So for any x, small x, that belongs to this set of arguments, there exists. Okay. So this E flipped means exists. A unique value from the set of values. Okay? Now, I'll give you an example, okay? So what does it mean? So this is not a vacuous definition. It actually makes a lot of sense, and it's actually quite restrictive. So let me give you 2 examples. So one example would be this. So I'm just going to write a function. Okay? So I will have the axis of arguments. Here I'll have 0. Okay, and I'm going to have axis of values, so y-axis, right? And maybe let this be my function. Okay. Typically, we denote it as f of x. Okay, so f is the name of the function. Oh, thank you. Now, can you please blank it? Wonderful. Thank you. That's a function, right? Now, let me give you an example of something which is not a function. X, y, and this stuff is not a function. So, can you guys tell me a difference? Do you see the difference between the two? Yeah? So what's the difference?
If it is a function for any x, there's only one y value.
Exactly. And what happens here?
There are
There are two,
two.
right? I mean, in this case, there is one here, and but just the only 2 points. So basically, here there exists an x, right, for which there are 2 y's. So that basically violates the definition of the function. So this unique is very, very important. Okay, so that's why it's not a trivial definition. Okay, it's something to keep in mind. So whenever you have a function, basically unique correspondence. Now, functions can be continuous, right? So basically, continuous function is the function that we can pretty much draw without taking our hand out of the board. So this is a continuous function, example of a continuous function. Functions can be discrete or discontinuous. So here is another example. So maybe something like this. So I'm going to use similarly shaped function, but maybe at some point it's going to have discontinuity. Okay? So this function is continuous. And this one is discontinuous. Now, this is a somewhat nasty function because of this break, okay? But you should be aware of such things. By the way, note here how I define it, right? So basically, in this point, the value of the function is here. But if you approach this function from the left, you'll see that it approaches, and the value of the approaches is actually different. So basically, the limit of the function, from the left is this value, right? And this is the value that actually takes. Have you guys heard about limit? Yeah? Who have heard about limit? Who has no idea what limit is? No limits? If that's the only idea that you have about limits, then we need to stop. So limit, have you heard about limit? So basically, here the limit of this function from the left is this value, right? But actually the value of the function itself is here. So that's just an example of discontinuity. Now, what else can we say usually about functions? Functions can be monotonic. So what does it mean for a function to be monotonic? Well, basically either decreasing or increasing, or there is this notion of weak monotonicity, which can be said as non-decreasing or non-increasing, right? So here's an example. So function like this. Maybe I'm probably going to start here. Okay, and this function, so x, y equals e to the power of x, right? So just exponential function. So what do we know that if x equals to 0, takes value of 1, and then it sort of increases. Okay, so this is basically strictly increasing example of strictly increasing function. Okay. Or we could say strictly monotonic. So monotonic basically means that it can be either increasing or decreasing, but that's basically what it means. Now, so this is strictly increasing. Now there could be a weakly increasing function. That would be an example. Okay, 0, x, y. So function like this. So say it stays at 0 up until some point a, then it goes linearly, and say it reaches 1 at some point b, and then it stays at 1. So that would be non-decreasing function. Okay, or it's weakly monotonic. Now, functions can be of one variable, functions can be multivariate, right? So far we've been talking about functions that just have one argument, in fact, right? Question?
Yeah, what did you write in parentheses under there? What does it say?
Weakly monotonic.
Okay.
Yeah, guys, if there are any questions, like about my handwriting, you know, anything, just kind of make yourself notice. So, like I said, functions can be of one variable, so these are simple univariate functions, right? So one variable, univariate. Functions can be multivariate, so, and usually those have very nice pictures. So something like this. Something like this. So if you have three-dimensional space, so and maybe your function is z equals to x squared plus y squared. Right, so if you want to plot this function, so that would be your x, that would be your y, that would be your z. Right? So this will be, first of all, if those two are zeros, right, so z equals 0, and so that's a point. And then if it's, so if one of these is actually equal to 0, right, then z equals x squared. So it's basically going to be like a parabola. And here it's also, if x is equal to 0, z equals to y squared, so here it's also a parabola. But what it is really, it's just kind of this, it's called paraboloid. Okay, so it's three-dimensional parabolic function. So let me try to draw it neatly. So it will look something like this. Okay, so. And that's how it's going to look like. Okay. So basically this kind of, you know, like a bullet, right? Any questions? Now, just to confuse you a bit even further, okay, functions can be not only multivariate, the values can be vectors, okay? So, in fact, nothing precludes you from defining a function on the space of vectors. And that's totally fine, so I can write something like this. F, vector function of vector x, is equal to 2x plus e. So basically, it's 2 times vector x plus unit vector. Okay, vector with all ones. And okay, I'm going to keep it like this, just to give you a feel that functions are pretty general creatures, okay? But from now on, we're going to focus on real functions. On real, univariate functions. So basically those examples that I've given you before. So simple functions that you can actually draw on two-dimensional plane. Okay? So those called real univariate functions. Any questions so far? For these functions, that are real, univariate, I'm going to